This one will be a little bit tougher form of a mixing problem in differential equations. I'm looking at Blanchard's Differential Equations book, 4th edition, in section 1.9, number 25. It says there's a 400-gallon tank that initially contains 200 gallons of water containing 200 parts per billion by weight of dioxin. Suppose water containing 5 parts per billion flows into the top of the tank at the rate of 4 gallons per minute. The water is kept well mixed, and 2 gallons per minute are removed from the bottom of the tank. Okay. So we have some kind of a tank. We have addition of 4 gallons per minute on top and removal of 2 gallons per minute on the bottom. The interesting thing here is that there's more going in than is coming out. So eventually this tank would overflow. So we need to keep track of that. Let's see if they ask us about when that happens. Oh, yes, they do. The very last sentence in question 25 says, how much dioxin is in the tank when the tank is full? So we need to know when that happens. So V initial is 200 gallons, but V maximum is 400 gallons. And if T is equal to the time in minutes, then the formula for the volume would be V initial plus 4 gallons per minute times T minutes minus 2 gallons per minute times T minutes. And what happens is the minutes can cancel, and this initial volume is in gallons. And when minutes cancel, this middle term is in gallons. And then when minutes cancel here, this last term is in gallons. So we get a formula V naught plus 4T minus 2T, and that'll just be V naught plus 2T. And since V naught is 200, this will be 200 plus 2T. So we know the volume that's inside of that tank at any moment in time. Now, we also could figure out at what moment in time we get to the condition that they're calling full. What they mean by full is that V is equal to 400, but V also has to equal 200 plus 2T. So if we try to solve here, we can minus 200 from both sides. We get 200 is equal to 2T. So if we divide by 2, T is equal to 100 minutes. So I've already used up a lot of paper, not even getting to the differential equations part. Okay, so the concentration that's used is 2 parts per billion for the initial at time 0, and then 5 parts per billion for the input. And then we don't even know what the parts per billion are for the output. What we'll do is we'll try to express the amount of dioxin in the tank as A for amount. A actually means A of T, and that'll be the amount of dioxin in the tank. Now, we're getting volumes in gallons, but we're getting concentrations in parts per billion. It will be a little bit awkward, but one thing that we could do is we could express the amount of dioxin in the tank by multiplying the volume by the concentration. For example, the initial amount in the tank, which could be written as A naught or A at times 0, could be expressed as, let me see here, 2 parts per billion times 200 gallons. And you get this very strange expression, 400 parts per billion gallons. So if you're having to deal with a number like this, then if you need to find the parts per billion, you'd have to divide off how many gallons were in there. Or if you knew how many parts per billion that was, you could divide that off and get how many gallons of mixture would be involved. So we're going to use this later on when we have to find unknown constants. And this is actually teaching us how we're going to interpret the answer at the end, because we'll probably get amounts as parts per billion gallons all the way through. But they probably just want to know, how did they ask that question? The question was, how much dioxin is in the tank when the tank is full? They probably just want to know the parts per billion in the tank when we get to t equals 100. Okay, so now let's try to find a way to express the rate of change of the amount of dioxin. Am I losing track of stuff off the top here a little bit? Yes, I am. Okay. So in this class, we're going to be interested in the rate of change of something with respect to time. Now, for the input, we're having 4 gallons per minute. So we'll do positive 4 gallons per minute. And then they went and told us that the input has 5 parts per billion. However, for the part coming off of the bottom, we're losing 2 gallons per minute. So because it's decreasing, I'll subtract and I'll say 2 gallons per minute. And then this is a little bit awkward because we don't know what our parts per billion are inside of there. So the A is going to stand for how much dioxin is in the tank. And as I was saying a moment ago, we're going to be keeping track of that amount of dioxin in these crazy units, parts per billion times gallons. So what I'll do is I'll try to conversion A in parts per billion gallons. And then we are in a little bit of trouble here. We would need to know how many gallons are in the tank so that we could divide that off. But if I'm not mistaken, I already found that. That turned out to be 200 plus 2t. And when I said that, I meant 200 plus 2t gallons. So we're going to bring that into this work now. 200 plus 2t gallons. And what happens is the gallons are canceling, and I'm getting parts per billion for this factor. And I'm getting gallons per minute times parts per billion, just like I had here. Okay, so this is a mess, but we can clean that up a little bit. dAdt is equal to 4 times 5, which is 20. Now in this one, we get 2 over 200 plus 2t times A. And we're minusing that. 2 over 200 plus 2t times A. And this is very close to what they call a first order linear ordinary differential equation, because we have a derivative to the first power, and then we have a function of the independent variable times our dependent variable to the first power, and then we have some other function, which in this case is the constant 20. To make the math a little bit easier, I think I'm going to simplify this. This is 2 times 100 plus t. And then this 2 and this 2 cancel and leave a 1. Now, what they usually explain is that when you have a first order linear, you can bring the a term over to the dA dt side. So we could easily rewrite this as dA dt. And when I move this to the other side, I'm actually going to change the sign on that term because I add the whole term to both sides. I end up with plus 1 over 100 plus t times a is equal to 20. So once we have it in the proper form, they teach us that this is, I think in Blanchard's book they call this A and then they call this B. This is in the proper form so that you can find a special function called the integrating function. They call it mu. Mu is equal to the integral, mu is equal to e to the power of the integral of little a dt. So we get e to the integral of 1 over 100 plus t dt. Now this is really a u substitution from calculus where the denominator would be u. But if you'll notice, the derivative of 100 plus t would just be 1. Or actually 1 times dt, and we already have that. So if this is the u, then this right here is the du. And the integral of 1 over u du is the ln of the absolute value of u. So what we get is e to the ln of the absolute value of 100 plus t. And the e and the ln cancel. And you get 100 plus t for your value of mu. Now, this can be finished a long way and a short way. The long way would be to multiply this, and this by mu and show that the left side is an exact derivative of a product rule. And then you'd have to integrate the right side. But most teachers will show that you can use this mu to sort of cut to the answer. In this case, you would have the formula for a is 1 over mu times the integral of mu times b times dt. Therefore, the mu is 100 plus t. We will have 1 over 100 plus t times the integral of 100 plus t times b, which was 20, times dt. Now I'm probably going to take this 20 out front, and I get a is equal to 20 over 100 plus t multiplied by the result of integrating 100 plus t, which is 100t plus t squared over 2 plus c. A person could actually distribute this through all three of those terms, and they might get something like 20 times 100t is 2000t over 100 plus t. Now, when the person multiplies the 20 by the t squared over 2, the 20 and the 2 will cancel into a 10. So we'll get 10t squared, but it will still be over 100 plus t. And then there will be a 20c over 100 plus t, which is really c over 100 plus t. So we're getting to the point now where we might be able to figure out the value of c if we knew an initial condition, like how much dioxin was in the tank and at what time did that happen. I don't know if I wrote it down. I think I didn't. But the initial amount in the tank was 200 gallons. And they told us that, oh, here it is. I wrote it down here. The amount of dioxin in the tank at time 0 is this crazy expression, 400 parts per billion gallons. So I think that what I'll do is I'll take this result and I'll say that when t is equal to 0, A is equal to 400 parts per billion gallons. So we get 400 parts per billion gallons is equal. Now, that t equals 0 is going to come in very handy. We're going to get 0 plus 0 over 100 plus 0. And that is going to be 0 over 100 is 0. And then we will have c over 100 plus 0. So we get 0 plus c over 100. So this whole mess is equal to c over 100. So you can solve that by timesing by 100 on both sides. And these cancel. So we get c is equal to 40 thou. And that brings us back to this thing. So this c right here is equal to 40,000. Now, if this is our formula, 2000t plus 10t squared over 100 plus t plus 40,000 over 100 plus t, we could even combine these together if we wanted, since they have the same denominator. We'll just leave it the way it is. They were asking us a question. In this problem, it was asking how much dioxin is in the tank when the tank is full. If I'm not mistaken, I found out that to have a full tank, you would have t equals 100 minutes. So what we're really going to try to figure out here is what is A at 100 minutes. So our formula for A is actually this thing with the 40,000 plugged in. And we would get 2,000 times 100 plus 10 times 100 squared over 100 plus 100 plus 40,000 over 100 plus 100. I'm being a little silly now. The bottom is definitely 200. So the top is 2,000 times 100 plus 10 times 100 squared. I get 300,000 plus 40,000. So we get 340,000 divided by 200. We get 1,700 parts per billion gallons. But when the tank is full, I messed up. Okay. When the tank is full, there will be 400 gallons in the tank. So if I get 1,700 parts per billion gallons, and if I divide that by 400 gallons when it's full, I get parts per billion. So let's see what that is. 1,700 divided by 400. Oh no, I want to get that back. 4.25 parts per billion. So that's how much dioxin concentration will be in the tank when the tank is full.